Okay, so the focus of today's lesson is the different ways that we can evaluate definite integrals. Just a reminder, a definite integral is an integral that has a lower limit and an upper limit, so we can interpret those as areas. The answer to a definite integral is a number or a value. So we've already been evaluating definite integrals, but I want to go through the different ways that you actually see a definite integral. So the first way is, if you're given a function in a graphical form, right? So just like this example here, we already went through this example, but you can interpret a definite integral as areas. And you can use areas to evaluate definite integrals. So that is the first way. So here in this example, you're given a function. I've already gone ahead and found the areas of the different segments. So you have a yellow triangle, a half circle, a green triangle, and a blue triangle. So the integral from -7 to 0, keep in mind you're integrating there from left to right. So anything below is negative, anything above is positive, would be -2.5 plus pi. Part B, the integral from 5 to 2. Notice now you're integrating from the right, 5, to the left, where you end at 2. So the way I would do this, if you're integrating from right to left, it's going to be the negative of what you would get when you integrate from left to right. So I would just say everything above is positive, everything below is negative. So I would take 3.75, subtract 0.25, and whatever your result is, take the negative of that. So in this case, it would be -3.5. That's probably the easiest way to evaluate definite integrals from right to left when you're given, when you're interpreting the graph as areas under the curve. Part C, the integral from -7 to 5. Okay, this one you're integrating from left to right. So anything below is negative, anything above is positive. So -2.5 plus 2 pi plus 3.75 minus 0.25, and I think if you add those up you get 2 pi plus 1. Part D, we've seen this before, the absolute value symbol. So the integral from -7 to 5 of the absolute value of x just means that everything is positive. Okay, so all the negative portions get flipped up, and really everything is above the x-axis now. So you would just be adding 2.5 plus 2 pi plus 3.75 plus 0.25 to give you 6.5 plus 2 pi. So that's it. That's how you use areas to evaluate definite integrals. The next way to evaluate definite integrals is to use approximation methods. So sometimes the function is not presented in a graph or in the form of an equation, but rather the function is given to you as a table of values. So if it's given to you as a table of values, you can use approximation methods. So what does that mean? That means you can use LRAM, RRAM, midpoint rectangular approximation, or trapezoids. So approximate the integral from 0 to 3 using LRAM. Okay, so we would use 6 subintervals for this question. The width is a half. It's a uniform partition. So we just write our W 0.5 times the function value at each point except for the last one if we're using an LRAM. Okay, and if I do that, I get 12. Now the midpoint approximation, here we can't use 6 subintervals. We have to use 3 subintervals, okay, with the width of 1. And this would form, at 0.5, that would form the midpoint of this subinterval. Okay, and then 1.5 at x equals 1.5, that would be the midpoint of the second subinterval. And then for the third subinterval, we would have that as the midpoint. And that's really all we can do given that data set using MRAM. That's basically our only option. So the width in each case there of each subinterval is 1. So I'm going to take that 1 and multiply it by the y value at 0.5, at 1.5, and 2.5. So I just add 4 plus 7 plus 1, multiply it by the width of 1, and I get 12. Next is the trapezoidal approximation. Okay, so I've used a shortcut here. It's the width of the, again, for this one, we're using 6 subintervals. Okay, so it's the width, which is 0.5, the same as in part A. Now, if we're using trapezoid, we're going to take that W and divide by 2. And then I'm going to multiply that by the first Y value, 2 times each of the other Y values except for the last one, and then plus the last Y value. Okay, so it's always the case. The first and last plus 2 times everything in between. And if I do that calculation, I get 12.75. So I can approximate that integral from 0 to 3, and it's 12.75. There was another way I could have done that trapezoidal approximation. So I've already found LRAM in part A. If I can find RRAM, then really all I need to do is average LRAM and RRAM, and that would be the trapezoidal approximation. So I've done the right rectangular approximation here. It's a width of 0.5 multiplied by each of the Y values except for the first one. And I got 13.5. So if I take 13.5 and average it with 12, which is the left rectangular approximation, I do get 12.75, which is what I got using the trapezoidal approximation. So you can use any one of the 4 approximation methods to evaluate definite integrals, to approximate them when you're given a table of values. Any questions on any of that? Okay, that brings us to how do I evaluate definite integrals when I'm given the function. So we've already done this too, but I want to do it in a little more depth. The integral from a to b of f of x dx, what that means by the fundamental theorem of calculus is just find the antiderivative, sub in the right end point or the upper limit, sub in the left end point, which is the lower limit, and subtract the 2 values. So we've done this before. Sometimes it's written as the integral from a to b of some derivative function is equal to the original function evaluated at b minus the original function evaluated at a. And there are some examples here. So the first one, and we're going to be using the calculator here so to verify the answer. The integral from -1 to 2 of 3x squared. So what does that mean? It means find the antiderivative of 3x squared And then whatever that is, sub in 2 and sub in -1. So we've got a new sort of notation here. That's what this means that I'm highlighting right now. That is the antiderivative of 3x squared. It's x cubed plus a constant. Okay? And then I've drawn a vertical line with the upper and lower limits attached to it. So what that vertical line means is take what's in front of it, your antiderivative, sub in the 2 first, then sub in the -1 and subtract the 2. So you get 2 cubed plus c when you sub in the upper limit, and you get -1 cubed plus c when you sub in the lower limit, and you need to subtract those two. So that gives you 8 plus c plus 1 minus c, which is equal to 9. And I've highlighted there that the c disappears. The c is always going to disappear when you're evaluating definite integrals. Always. It will always disappear. So common practice is to not even write down the c when you're evaluating definite integrals, to save you a little bit of time. It's not wrong if you do, but if you do enough of these, you'll notice the c is always going to disappear. So why bother? Okay, so we've evaluated that integral and we got 9. Okay, again, notice 9 is a value. We're evaluating definite integrals. That 9 can be interpreted as an area. Okay, so before I go on to the next one, you can verify this using the calculator. And give me a minute, I'll share my calculator with you. Okay, so here's the calculator. How do I evaluate definite integrals on my calculator? So first of all, turn the calculator on and go to the y equals, like as if you were graphing a function, and just enter the integrand. So 3x squared. Okay, so make sure you got 3x squared in there. Then I exit that screen. And the function we're going to use is math 9. So hopefully when you have it, you have a calculator that you see the integral notation when you hit math 9. Just type in everything you see there as is in the boxes. So the lower limit is -1. The upper limit is 2. Now, what's our integrand? Well, we got to go vars, y vars, and select the function where we put 3x squared, which is in y1. And we're integrating with respect to x, so make that an x. And then just hit enter. And you get the value of the definite integral, which matches what we got. Any questions on that? So it's just math 9. Okay, next example. The integral from 0 to pi of 2 cos 3x. So my first step would be to pull that 2 outside the integral sign so that my integrand is just cos 3x. Okay, so now what does that mean? I'm going to find the antiderivative of cos 3x, which is 1/3 sine 3x. So I'm going to multiply that by 2, and I end up with 2/3 sine 3x. Okay? And I'm going to evaluate that at pi and evaluate that at 0. So I've drawn a vertical line with a pi and the 0 attached. And that notation means sub in the pi into the function, sub in the 0, and subtract the two values. So you get 2/3 the sine of 3 pi minus 2/3 the sine of 0. Well, the sine of 3 pi and the sine of 0 are 0. So that integral, that definite integral, is 0. So if I go back to the calculator, I'll just take you through that one more time. Maybe I'll do it slightly different this time. Okay, you don't necessarily have to put the function into y1 or into this list here. You don't have to. That's the way I showed you the first time. The other way to do it is just go math 9. Okay, and you can type the function in here. So I'll put in my limits, 0 to pi. And then just type in 2 cos 3x dx, just like that. Hit enter, and your calculator spits out that garbage, 4.778 times 10 to the negative 14, okay, which is effectively 0. 10 to the negative 14, that's pretty small. So we've got an answer from the calculator of 0, which validates what we did manually there. Any questions on that? Okay, and notice in that example, I didn't write down the plus c for my antiderivative because the c's are going to disappear when I sub in the pi and the 0 anyways. So I left out adding the c to the antiderivative, and I will from now on. Next example, the integral from 0 to 1 of 3x plus e to the 2x minus 1. So this amounts to finding the antiderivative of 3x, then finding the antiderivative of e to the 2x minus 1, adding them together. Okay, that would be the antiderivative, and then I would have to evaluate at 1 and evaluate at 0. So it looks like I forgot the vertical line there. There should be a vertical line here. Okay, so the antiderivative of 3x is 3x squared over 2, or 3 over 2x squared. The antiderivative of e to the 2x minus 1 is e to the 2x minus 1 divided by 2, or multiplied by a half. Take that, sub in 1, which is the first large bracket there. Take 0 and sub it into that antiderivative and subtract the two values. So after a little bit of simplifying, I get 3 plus e over 2 minus 1 over 2e. Okay, I found a common denominator there, which is 2e. And I end up with e squared plus 3e minus 1 divided by 2e, which I typed into just a normal calculator, and you get 2.675. You can verify that using the definite integral function on your calculator. It is indeed the same thing, 2.675. Any questions on those first three examples? Again, notice I didn't put the c in there when I was finding the antiderivative. Okay, so the first three examples the integrand of each one of those integrals is fairly straightforward. We didn't need to use any fancy integration methods like substitution or completing the square or long division. But I need to show you what happens if I've got an integral, a definite integral requiring substitution. So this example here is a pretty straightforward integral requiring substitution. But we need to make sure that if we're going to substitute and turn this entire integral into an integral in another variable, and what I mean by that is we're going to convert that into an integral of u, that's what we've been doing all along with substitution, then we also need to convert the limits of integration, because those limits of integration, the 0 and the 3, are meant to be for the variable x. So if we convert the function into something in terms of u, we need to convert the limits into u as well. Okay? So I'll take you through that. We let u equal 4 minus x, then du by dx, the derivative of that is just -1. And so I can substitute dx with negative du. Okay? And the integral from 0 to 3 of 1 over 4 minus x dx would be the integral of 1 over the square root of u times negative du. But you'll notice there that the limits have changed to 4 and 1. So how did I get that? Well, I got that by using my definition for u. So I'm going to use this u equals 4 minus x to get my new limits. So my original limit, 0, when x was 0, if I sub that into my expression for u, I would get that u is now going to be equal to 4. And my original upper limit, which was x equals 3, when I sub that into my expression for u, I get a new limit of u equals 1. So the integral is no longer from 0 to 3. It's the integral from 4 to 1 of 1 over root u times negative du. The rest is just finding antiderivatives. So I take the negative outside and I rewrite the expression without the square root sign. And then you can see that I flipped, in the third step there, the integral becomes positive because I've flipped the direction of integration. I changed it from 4 to 1 in the second step with the negative outside the integral to 1 to 4. And when I do that, I just multiply by a negative, so the negative outside disappears. So I've reversed the direction of integration there. Maybe I'll write that down here. You don't have to do that. The main reason I did it is that it gets rid of the negative sign. That's really the only reason I did it. Okay? You do not have to have the 1 at the bottom and the 4 at the top. We could have done it with the 1 at the top and the 4 at the bottom. I just did it to get rid of the negative sign. So I find the antiderivative of that. Which I didn't do right, did I? What is the antiderivative of u to the negative 1/2? It's u to the 1/2 divided by 1/2, which is 2 u to the 1/2 evaluated at 4 and 1. I just forgot to write the 1/2 in that step. So now we take 4 and sub it in there, take 1 and sub it in there, subtract the 2, and we end up with a value of 2. Any questions on that? Again, notice I didn't add a constant when I found the antiderivative, and that's because the constants will always disappear when I sub in the upper and lower limit and subtract the 2. Okay, one more example with an integral requiring substitution, but it's the same, actually 2 more here. It's the same idea. Okay, for the first one, let u equal x squared plus 1. The derivative of that is 2x. So I can substitute x dx with du over 2. And my new limits of integration using my definition of u here, so using this, my new limits become 1 and 5 rather than 0 and 2. And so that integral becomes the integral from 1 to 5 of u cubed times du over 2. I can take the 1/2 outside the integral sign. Then I find the antiderivative of u cubed, which is u to the 4th over 4, which I can simplify to u to the 4th over 8, and I'm going to evaluate that at 5 and 1, and when I do that and subtract the 2 values, I get 78. The last example here I'll leave for you to do or to complete. I've already started it by letting u equal x squared plus 4x plus 7. The derivative is 2 times x plus 2, which means that I can substitute the x plus 2 times dx in the integrand with du over 2. My new limits would be 7 and 28. So I'll leave that with you to try and hammer that out manually, and then please use your calculator to verify that you did in fact get the right answer. So I'll leave that one with you to finish, and you can check it with your calculator. Now, one other word that I want to say here about integrals and the different ways that you can evaluate integrals. Sometimes you may get an integral where the function is so complicated and difficult to integrate that you wouldn't be able to do it by using any method of substitution, any method of integration like substitution or like completing the square or using some table of integrals. You wouldn't be able to do it. So in those cases, when the function looks impossible or seems impossible to evaluate, you can always use approximation methods. Okay, so approximation methods, LRAM, trapezoid, etc., can all be used to evaluate or approximate any integral. You just need to use as many subintervals as you can and a powerful computer. So there are programs that will do that. Okay, you want to basically let the number of subintervals go to infinity. The more subintervals you use, the better your approximation would be. So that's the benefit of being able to use these approximation methods, because they will also allow you to find definite integrals when you have no idea how to integrate. Okay, that brings us to the last part of the lesson, is how do I deal with functions? Can I integrate a function that has a discontinuity? So by discontinuity, I mean a hole or a jump or a vertical asymptote or something like that, right? So there's this concept of a function being bounded. You can read the definition there, but a picture's worth 1,000 words. If you look at that first diagram, you have a blue curve, and you have a y value of m where they've drawn a purple line, and a y value of negative m where they've drawn another purple line below the function. You can see that from between a and b, that function is bounded. It's between m and negative m. Okay? Any function that's bounded like that, we're going to see that we can integrate it even if it has discontinuities. This second diagram here, you can see we got a vertical asymptote there. Okay? This function is not bounded. You cannot bound this function because it extends to infinity and negative infinity. So between a and b here, this function, we can't really write that this function is bounded because it goes off to infinity and negative infinity. So whenever you have a vertical asymptote, you cannot integrate across a vertical asymptote. Which brings us to this last theorem here. This is the important part. Let f be a function defined on some closed interval between a and b. If f has finitely many discontinuities but is bounded, then f can be integrated. So what that means is if you can count the number of discontinuities between a and b, and the function is bounded, then you can integrate it. If it's not bounded, then you can't integrate it. So long story short, even if it has holes or jumps, you can still integrate a function, but if it has vertical asymptotes, you can't. So here's a few examples. The first one, I've colored in everything, but the first one was a function from -2 to 8, and we want to integrate that function. But there's a hole at 2 and there's a jump at 2. But you can still integrate this function because it's bounded and it has a finite number of discontinuities. You just treat the function as if there was no continuities. No discontinuities. So this one here we can integrate using geometry or shapes. So I've colored in the different shapes. And I can write that the integral from -2 to 8 is just the area of all those shapes, keeping in mind that area above will contribute a positive number to the definite integral, and areas below contribute a negative number. So we can write the area of the yellow rectangle is 8. Then the purple triangle is base times height divided by 2, so 1 times 1 divided by 2. The blue triangle, base 4 times height 4 divided by 2. And the purple or pink triangle there at the end, which will contribute a negative number, is 2 times 2 divided by 2. So we get a value of 17.5. Okay, even though there is a jump there at x equals 2. It's a little bit difficult to see because I've colored everything in. But if you look at the printout, you'll see that there's a jump there at 2. But we can still integrate it. The next question, you're given a piecewise function and asked to graph it and evaluate the integral from 0 to 6. So this is another function that has a jump at 2. There's a hole there as well. You can still integrate that function using geometry. It's just a triangle and a rectangle, and we get a value of 22. So the point is, even though I've got a discontinuity, because that function has no vertical asymptotes, it's bounded, it means I can integrate it the way we've been doing all along. This example here, the last one, okay? the integral from 1 to 4 of x squared minus 9 over x minus 3. If we factor the numerator, we see that this function has a hole at x equals 3, even though I didn't write that. Maybe I should write that. There is a hole at x equals 3. Well, 3 is in between 1 and 4. But since it's only a hole, not a vertical asymptote, I can still integrate that function as if the hole wasn't even there. So I find the antiderivative of x plus 3, which is x squared over 2 plus 3x. Draw my vertical line with the 4 and the 1 there. And now I substitute in the 4. I substitute in the 1. Subtract the two values, and I get 16.5. So even though the function has a hole on the interval of integration, in other words, the 3 is in between 1 and 4, I can still integrate because there's no vertical asymptote. Any questions on that? Any questions on anything we've covered today? Or anything else for that matter?